to have the chance to address you on this special occasion. The title of my paper is Iris Recognition based on few-shot learning. And the outlines of my talk are as follows. The first part is introduction. Iris recognition is considered to be one of the most reliable and accurate biometric features and have many advantages over other biological features such as face fingerprint, which makes it widely recognized in biometric systems with high reliability and accuracy. With the development of advanced computing hardware and the availability of big data, deep learning technologies have been applied to many areas, including iris recognition. When a sufficient amount of labeled data is available, the iris recognition approaches based on deep learning are able to achieve good performance. However, given a limited number of training symbols, these methods may result in overfitting. To tackle the overfitting problem, in recent years, research on few-shot learning, that is, learning for the problems of insufficient sample size, has attracted widespread attention. In the context of iris recognition, those overall sample size of data sets is considerable. The specific iris images of each person are generally only about 20, which is relatively small compared to other types of data sets. Some deep learning-based methods rotate the original iris images by various angles to expand the sample size. However, this approach does not increase the diversity between each sample and consequently has limited effects on preventing the overfitting issue. Inspired by the advantages of few-shot learning on addressing the issues caused by small samples, in these papers, we propose a few-shot learning approach based on the model agnostic meta-learning method. We named the proposed approach as improved mammals or Mammal to adapt mammals for iris recognition. Our experiments on the benchmark datasets shown that mammals perform better than mammals and achieves competitive performance when compared with deep learning based approaches. The second part is mammals. Mammal is a model independent meta-learning algorithm that can be used for various learning problems and models based on gradient descent. Unlike the previous meta-learning methods that requires learning update functions or learning ruler, Mammals neither increases the numbers of model parameters nor sets any restrictions on the structures of the model. Mammals can easily interact with a fully connected network, convolutional network, and so on. The training of mammals algorithms takes task as the training unit, and the corresponding dataset is divided into training site, verification site, and task site. The whole algorithms is divided into meta training phase and meta test phase. In the meta training phase, select the tasks from the given distributed TI, where each task contains k categories, and each category contains n samples. Meta learning tries to obtain a good generalized models by training all tasks, which can quickly adapt to new tasks. In the meta training phase, first use the training set to obtain the loss values of the original model parameter set on TI, and then use gradient descent to obtain theta i's, which you can see in the Formula 1, whereas alpha is the meta training learning rate used in the in the inner loop. The test site d-test is then used to verify in the expected parameters set i's, thus obtaining a new loss, middle loss. The loss values here can only be regarded as a part of middle loss, and the cumulative sum of middle loss is calculated after the entire internal loop is the final middle loss. Calculate the gradient of the total loss and do stochastic gradient descent to update the original parameters values of the model as Formula 2, where beta is the learning rate used in the outer loop. Figure 1 is the Mammal's visualization. The third part is our approach to improve Mammal. The Mammal network architecture was originally derived from the embedded function networks architectures used by Vinyals et al. This network architecture has the standard configurations of convolutional neural network commonly used in image classification tasks, as shown in the Figure 2. With the network model balls, Mammal can be directly applied for error recognition, as demonstrated in the experiment sections. However, to generalize the model, improve the performance of the models in multi-task trains, and further elevate overfitting, we improve Mammals in the following two aspects. First, as shown in the Figure 2, the network models of Mammals used for image classification contains 4 layers of convolutional neural network. Through experiments, we have found that the following structures with addition of 2 more convolution modules provides the best performance on error recognition. The compositions of the 2 newly added models is same as the composition of the previous models. Expect that the maximum polling process is not performed. The details are shown in Figure 3. To reduce the overfitting problems in the training process and improve the generalizations of Mammal to adapt to new tasks, we have introduced regularization constraints in the loss functions and added L2's regularization on the basis of the original cross entropy's loss, and shown in the Formula 3, where omega is the parameters for regularization. The corresponding algorithms is outlined in algorithm 1. The first part is experiments and results. 4.1 size and parameter settings. The error size used in our experiment come from the free and open database Cassius V4.0 of the Institute of Automations of the Chinese Academy of Science and the public error imaging database GLU V1.0 of Jilin University, and the error images need to be pre-processed. Details are shown in the Figure 4. Next is the evaluation metric. To measure and evaluate the performance of mammals and the method used for comparison, we use the most common neural network evaluation indicators, the accuracy rate. The accuracy rate represents the ratios of the correct numbers of predicted samples to the total numbers of samples. 4.3 is the comparisons of mammal and non-mammals. Both mammal and non-mammal use the 3 datasets. Cassius interval, lamp and GLUV 1.0 for trainings. In the training phase, the number of iterations is uniformly set to 20,000 steps, and the verification is performed every 500 steps, and the middle batch size is uniformly set to 2. That is, one iteration contains 2 tasks. The specific parameter setting of the mammals and enhanced mammal training phase experiments are shown in Table 1. Table 2 shows the result of a 5-way 1-shot and a 5-way 5-shot on Cassius intervals, lampos, and GLU decides for mammal and mammal. It can be seen that overall, the experiment result of mammals on the 3D sites are better compared with mammal. And Figure 5 is the training accuracy and loss of mammals and mammals for different sites. As shown in Figure 5 above, we can see that mammals has a more stable training accuracy and greater fluctuation range than mammals, and it reaches the highest point more quickly, and mammals had lower training loss than mammals as a whole. Its converges faster. This provides the effectiveness of our mammals method. 4.4 is the comparison of mammal and deep learning based method for error recognition. We compare mammals and fuse representative deep network modules that are trained and tested on small simple error data. First, we pre-process the error images use the same approaches as in the section 4.1. During the training, the modules extract features of errors images and use the softmax layers to classify errors. We use the same datasets in 4.1. With these datasets, we use TensorFlow to train, verify, and test the models for error recognition. The train process uses cross interface as the loss functions and uses the stochastic gradient descent to update network parameters. The accuracy of recognitions is given in Table 3. And we can see that mammals proposed in these papers and mammals have considerable advantages in error recognitions when small samples are available for training. Next is analysis of parameters. 4.5.1 is network structures. We replaced the original mammals network with a simple convolutional network, ResNet network, and Inceptions network. Conducted experiments on the Cassius lamp dataset and compared their performance with mammal. Our experiment result below shows that mammals achieved the best result, as displayed in Table 4. The reason is that the mammals' training strategies will lead to complex calculation. Only shallow, uncomplicated neural network can be used as base learners. Complex networks like ResNet and Inceptions are easy to overfit during training. Next is network structures. We evaluated the influence of various input errors image size on the recognition accuracies by carrying experiments on the interval dataset. It can be seen from the result of Table 5 that the size 84 by 84 gives the best result, and the accuracy decreases with the increase of the size. This could be due to discriminative error features, and the size are better obtained. 4.6 is the invariance to rotation. When a person's errors was captured, the head of the persons may not be aligning with the collecting device, which may cause iris rotation problems. Deep iris night shows excellent invariance to this change, but in the case of sufficient samples provided for training, to study the influence of the iris images rotations to our method's recognition accuracy, we use the interval set and train it with non-rotating images. During the testing process, the test images were rotate in the range of -8 degrees to 8 degrees with a step size of 2 degrees. Deep iris night is selected to perform the same steps, but with small sample size. As seen in Table 6, our Mammal achieved much better results against the rotations of iris images. The last part is the conclusion. In these papers, we studied the iris recognition problems with limited train data. Based on Mammal's algorithms in media learning, we introduce L2 regulations on the basis of the original cross-entropy loss functions of mammals to improve the generations of the approach and avoid the overfitting. At the same time, in order to further improve the abilities of embedded network to extract features, we have improved the original network structures of mammals with the addition of 2 convolution modules. Experimental results show that the proposed method can effectively improves the accuracy of recognition and has considerable advantages compared with deep learning methods. In the future work, we will further explore the applications of other few-shot learning methods in the field of iris recognition. Thank you.